With the rapid development of LLM-enhanced visual analytics systems, users can now express their analytical needs via natural language and promptly obtain visualization results. However, due to the inherent ambiguity of natural language input, specifying complex interactions such as conveying visual patterns or selecting data ranges can be time-consuming and error-prone. Therefore, efficient and precise interpretation of users' analytical and interaction intents is crucial in generative visual analytics systems. In this work, we introduce InterChat, a generative visual analytics system that leverages multimodal interactions and LLMs to interpret users' analytical and interaction intent. We first explore the design space for applying multimodal interactions in VA systems via pilot brainstorming sessions and literature reviews, constructing the framework of design space for user intent, interactions, and language input. The interactions and language spaces are designed to complement each other, working interchangeably to improve the efficiency and accuracy of visual analytics. Building on this, we design a multi-agent-based LLM architecture that serves as a bridge between users and LLMs. InterChat incorporates multiple interactions, including click selection, lasso selection, box selection, and free drawing. We design modules including intent inference, prompt synthesizing, and response processing. These modules empower the generation of D3 visualization via effective prompt design and interpretation of user intents via vision language models. Now, we use the Steel dataset to demonstrate InterChat's capabilities. The dataset contains electricity consumption information of a manufacturing company. First, we instruct the system to display the change in power usage over the past year using a line chart with quartiles. Then, we use the box selection tool to select a portion of the data, zoom into this range, and increase the temporal resolution to 1 hour. Next, we use the free drawing tool to draw a line on the chart and instruct the system to apply a threshold to the data. Here, we want to compare the data with the leading and lagging power usage data. If unexpected results occur, such as improper axis ranges, we can directly instruct the system to fix the error. Finally, we want to use the load-level data as a reference. By drawing a rectangle on the chart, we instruct the system to add this information to the bottom of the chart using vertical bars. Next, we use Netflix stock price data to identify price patterns. We start by visualizing the stock price over the past year and drawing an upward arrow on the chart to let the system identify all the similar trends in the last 5 years. Using the selection tool, we select 2 temporal ranges on the x-axis and ask the system to compare the trading volume in these 2 time periods, which are displayed as 2 side-by-side bar charts. We then click on 2 days with the highest trading volume and instruct the system to compare the data using a pie chart. An additional chart showing close stock price data can also be added with follow-up instructions. Finally, we use the lasso selection tool to select visual components and let the system explain the reason for the discrepancy between trading volume and closing price. As a result, the system generates the visualization for the most recent 7 days, enabling users to observe the patterns. For more details and more cases, please refer to our paper and appendix.